Hello, everyone. My name is Karthik Vijayaraghavan, and I'm a DocumentDB Specialist Solutions Architect with AWS. I have been helping customers build solutions using NoSQL databases for more than 6 years now. I've had numerous opportunities to help my customers devise strategies and solutions for both, greenfield applications as well as migrations from other databases such as, relational databases or even document databases. In the digital economy, end users expect applications to be resilient and highly available. Amazon DocumentDB global clusters allows customers to build such resilient solutions to recover from regional outages. In this webinar, I'll provide an overview of global clusters and introduce you to an open source solution that we have developed to automate the global cluster failover process. And I'll start with the basics and provide you with an overview of Amazon DocumentDB and its architecture. I will also provide an overview of global clusters and how things work under the hood. I'll then discuss use cases for global clusters. So if you're new to global clusters, we got you covered. After getting you up to speed on global cluster concepts, I will discuss the reference architecture for the solution to automate global cluster failover process. We have open sourced this solution under Apache 2.0 license to help our customers like you simplify the failover process. And I promise I will share a link to the solution, to the source code towards the end of the session. I'll wrap up today's webinar with information on some of our recent releases. So let's get started here. What is Amazon DocumentDB? DocumentDB is a fully managed, scalable, MongoDB compatible database service. AWS manages tasks like provisioning and patching and allows our customers like you to focus on functionalities that matters to your business. Our cloud native architecture allows you to scale millions of requests per second with millisecond level latencies. DocumentDB is compatible with MongoDB 3.6 and 4.0, and this allows our customers to seamlessly migrate their MongoDB workload to Amazon DocumentDB with minimal to, in a lot of cases, no code changes. Let's talk about the architecture of this cloud native AWS service. DocumentDB is architected to separate storage and compute so that you can scale these components independently. The compute instances can be scaled horizontally or vertically, and they are distributed across 3 availability zones to give you high availability. And to maintain high durability, DocumentDB replicates data 6 ways across 3 availability zones in the distributed storage volume that you see on the slide. DocumentDB's architecture allows us to offload tasks to their respective layers. The replication task is offloaded to the storage layer so that your instances can be freed up to perform compute-heavy work such as query processing. Backup is another such task that is offloaded to the storage layer, further freeing up your instances to perform that compute-heavy work. Again, as a reminder, DocumentDB is a fully managed service. This means AWS manages the tasks of replication, backup, and so on, and ensure that the data is fully replicated, allowing you to focus on developing features that matters to your customers. So now that we saw how Amazon DocumentDB is architected in a single region, let's expand that concept out to global clusters. Amazon DocumentDB global clusters allows you to replicate data to up to 5 secondary AWS regions. And this replication is offloaded to the storage layer as well. This is a physical replication from the storage layer of the primary region to the storage layer of the secondary region. And since it's a physical replication, the replica lag is very low, typically less than a second. Global clusters allows you to recover quickly from regional outages, should they happen. If an AWS region goes down, you can promote a cluster in a secondary region to a standalone cluster that can accept writes. And this process typically takes less than a minute and is pretty ideal for applications with strict RTO requirements. Global clusters are compatible with DocumentDB engine version 4.0. So if you're running on an older version like 3.6, you'll have to upgrade to start using this capability. And when you deploy global clusters to all 5 AWS regions, like 5 secondary regions and 1 primary region, the maximum number of reader instances you can have across the globe is 90. So this will allow you to scale your reads globally. So as you can see in the slide, application 1 writes data to the primary region in the global cluster, and application 2 reads the data from the secondary region. Could be Tokyo, could be Oregon, or could be any other secondary region that you have added to the global cluster. Let's take a little bit closer look on what happens under the hoods. So let's say an application is writing data to the primary region, right? So here our application app1 inserts a document db.foo.insert1, a MongoDB API, and hence the MongoDB compatibility, right? So the application sends this write request to the primary instance. The primary instance then sends these log records in parallel to storage nodes, replica instances, and a replication server, right? Because it's a global cluster setup, and you have this replication fleet in the storage, along with the storage fleet now. And the primary instance sends these log records in parallel to the storage replication instances and replication server. The replication server then streams these log records to the replication agent in the secondary region, in our case here, Oregon. Right? Now, the replication agent will take these log records and send them again in parallel to the storage nodes and the replica instances of the secondary region. So now if you have an application 2 that is doing a read operation, db.foo.find, and looking for the x1, it's going to be able to read the document from the buffer cache of the replica instance there, right? So this process, like from 2 to all the way up to 3, it takes about less than a second. Right? So now let's take a look at some common use cases for global clusters, right? There are 2 main use cases: disaster recovery and data locality. Global clusters allows you to promote secondary clusters to primary for faster recovery in the event of a regional outage. So this capability makes it really ideal for DR use cases. You can also bring data closer to your users in different AWS regions to enable faster reads for globally distributed applications, making global clusters a great candidate for data locality use cases. Let's dive deeper into these use cases now. Let's start with the DR use case. Since the data is replicated in near real time, global clusters allows you to be up and running in a secondary region in less than a minute's time, if and when a regional outage happens. There is no data movement that need to happen when performing a global failover, and the time taken for recovery is just the time it takes to promote the secondary cluster to a standalone cluster. Also, for use cases where you want to migrate data across regions, those are pretty easily solved by global clusters as well. One of the important points to note here is the cluster topology. Now, your primary cluster will be running the required number of instances to satisfy your application's SLA and availability target, like 2 nines, 3 nines, and 4 nines, and so on. Since replication is offloaded to the storage layer, the instance count in the DR cluster need not match the primary region. So you can see here in this example that you have a DR cluster just with 1 instance, and you'll still get the low replica lag and high durability in the secondary region, right? So offloading replications to storage helps with cost optimization in addition to the low replica lag benefit that we already discussed. Now, if you want to scale your secondary cluster, it will take about 8 to 10 minutes, regardless of the data volume. Again, this is due to the decoupled compute and storage architecture. Now, I'm showing this slide with 1 instance in the DR region. Now, it's the replication is completely offloaded to the storage layer. So technically, you can run your DR headless, meaning you can run your DR cluster with no instances at all, right? Because since the instances do not participate in the replication process, you don't need to have replica instances in the DR region. However, one thing to keep in mind is when you run headless without instances in the DR region, certainly it helps to save cost, but it increases your recovery time objective, because when there is a disaster, you will have to spin up those instances, which can take anywhere between 7 to 10 minutes. So, you'll have to weigh your decision of running headless or not based on the time it takes to recover. But the architecture allows you to run a DR instance or DR cluster without any instances, allowing you to save cost. Now let's look at the second use case, which is data locality. Since replication is offloaded to the storage layer, there is little to no impact to your application's performance, as the application typically interact with the compute layer. The low replica lag that DocumentDB provides is because of that physical replication, right? I talked about like less than a second latency. This low replica lag enables you to use the secondary clusters to perform local reads. So you can now build globally distributed application that can read data from clusters that are closer to the end user's region, and you can avoid cross-regional latencies for those users, giving them a better experience. So we discussed about how global clusters work and what are the common use cases. Now let's look at how you can automate the failover process for Amazon DocumentDB global clusters. Here is a reference architecture for the first part of the solution, which is for disaster recovery automation. Now there is a prerequisite for this solution, which is basically you'll have to create a private hosted zone in Route 53 with a CNAME that points to the DocumentDB cluster endpoint. Using Route 53 is one approach to decouple your database endpoint from applications. Again, the idea here is to make sure that during a disaster, you don't have to make application changes as well. So we're just like, decoupling the database endpoint from application using Route 53. So you'll have to pre-create that before using the solution. This solution also uses DynamoDB as a key value store to track the inputs that you're passing to the solution, to maintain idempotency for Lambda function, just to avoid the Lambda function running multiple times. So we look at the input. If it is already in process, we just ignore. Also, DynamoDB is used to track the status of cluster promotion. So the solution that is depicted in this reference architecture allows you to seamlessly fail over to a healthy secondary cluster if and when AWS region hosting DocumentDB cluster is unavailable. And in this solution, we use AWS Lambda for triggering APIs for DocumentDB cluster management, as well as Route 53 APIs for endpoint management. As a customer, as an end user of the solution, you can define what the DR event is and let that DR event trigger a Lambda function that this tool provides. Now, in my experience with different customers, I've seen the DR event to be defined differently by different customers. So we give you the flexibility to define what that DR event is, and then you can just add that as a trigger to the Lambda function. So the first Lambda function in this tool is called failover to secondary. And it takes the global cluster ID that we are dealing with as an input, along with the secondary cluster that needs to be promoted. And it also takes the Route 53 hosted zone ID, which was the prereq, along with the CNAME that is used by the application. So that when the solution completes its job of for performing failover, it'll also ensure that the Route 53 record value is updated so that your application can seamlessly talk to the newly promoted database. So when your DR event invokes this Lambda function, it first removes the secondary cluster from the global cluster. Again, you provided the secondary cluster and global cluster as input. So it just removes that secondary cluster and promotes it to a standalone primary. The function then goes and updates Route 53 with the newly promoted cluster's endpoint. So let's say the database promotion takes about a minute, and it takes about 30 seconds to about 60 seconds for promoting or for the DNS propagation. So in less than a couple minutes, your application will be up and running, talking to the newly promoted cluster. Now, after this first Lambda function completes, you're going to be back in business, right? So in less than a couple minutes, your applications are now continuing to talk to the newly promoted cluster. So there is no more disaster situation. So you can define when that event is really complete, and then trigger a second Lambda function, which is convert regional cluster to global. And what this function will do is it will convert the newly promoted primary in the previous step to a global cluster. And this is basically required to ensure resiliency. This function also takes an array of secondary clusters that should be added to the global cluster as input. And as a net result, it converts the regional cluster to a global cluster with the secondaries that you have provided. So at the end of this function, you will be up and running with a global cluster, which has the primary cluster as what you provided as input to the failover to secondary function, with the secondary clusters that you provided as input to the convert regional cluster to global function. So now let's take a look at a demo to see how this DR automation solution looks like. Let's navigate to the AWS console and see the solution in action. Okay, so I'm here at the AWS console for Lambda functions, and here is our first Lambda function, failover to secondary. So I'm going to trigger this Lambda function, and while this Lambda function is running, let me explain what's going on here. So this Lambda function takes the global cluster ID, a global demo, as input, and it also takes a secondary cluster ARN to be promoted to a standalone primary. And here we have our primary cluster CNAME and the hosted zone ID from Route 53. So if you go to Route 53 over here, you can see that I have a CNAME called primary.sample.com, which I passed as input, which is right now having the record value as the cluster endpoint for the primary of this global demo cluster. And I also provided this hosted zone ID as input. Now let's go to our Amazon DocumentDB console and take a look at what this global cluster looks like. So we provided this global demo global cluster as input to our Lambda function. And this global demo global cluster has two clusters in it. The Ohio cluster in US East 2 has the role of the primary, and the Virginia cluster has the role of the secondary. So if I open my Virginia cluster here, you can see that this has a few instances in it, like it has 3 instances. And here is the ARN that I used as input to my Lambda function. Now, since I triggered the Lambda function, you can see that this cluster status is showing as promoting. And this process is what I said earlier. It takes about a minute's time to get the cluster promoted. Now, again, the important thing to note here is while this cluster is being promoted, there is no data that is transferred or moved between the primary and secondary. All that we're doing is we are removing the Virginia cluster from the global cluster called global demo and converting it into a standalone primary cluster. And whenever it is converted into a standalone primary cluster, your application can then start sending writes. Or in other words, the standalone primary cluster can accept writes. Now, important thing to keep in mind here is when you promote a cluster from a global cluster, when you promote a secondary cluster into a standalone primary, it's no longer a part of that global cluster. So the global cluster, global demo in this example, is not going to be replicating any data to the promoted secondary cluster after the promotion process is completed. So if I go back to my Lambda function, you can see that I also pass an input called is delete global cluster to true. Because this global cluster is not going to be replicating data, nor I can come back to this global cluster after, let's say, our East 2 region is up and running. I really don't need that global cluster anymore. So I pass this parameter as true just to go ahead and delete that old global cluster. Now, if you say false, it's just not going to delete it. But I prefer to delete the old global cluster, knowing that it's not going to do any further replication, nor I can go back to that cluster. So it looks like our Lambda function here completed. So I get a 200 successfully promoted cluster. So if I go back to my global cluster here and refresh the screen, I can see, I should be able to see that the Ohio cluster is in deleting status, and the global demo cluster, which we started off, is gone. We already deleted the global demo cluster. And if I switch to Northern Virginia region, which is the cluster that I said I want to, promote, I should be seeing that Northern Virginia cluster over here. So you can see that our Virginia cluster is now a regional cluster with its own primary instance, meaning we promoted the Virginia cluster to a standalone primary with its own primary, which can primary instance, which can now accept writes. So that's part one of our Lambda function, which is the failover to secondary. Now, by this time you have recovered from the disaster, right? So you are now able to write to the Virginia region for whatever reason. Let's say the Ohio was down, you're now able to communicate to the Virginia cluster and write to it. But what if Virginia goes down? Again, very rare, but what if it happens? So to build resiliency back, this second Lambda function can be triggered, and it helps to do that, right? So let's trigger this Lambda function, and let's take a look at what it takes as input. It takes the same ARN for our Virginia cluster, which is going to be the primary cluster in the newly created global cluster called global demo. It's gonna take a secondary cluster, array of secondary clusters as input, and it's gonna just create that global cluster for us. So if I go back to our DocumentDB console, if I see this and refresh this page, you can see that there's a global demo, global cluster created. Our Virginia cluster is now taken the role of the primary cluster within that global demo, and we have a Ohio 2 cluster now in creating status. And you can see that this Virginia cluster is in a modifying status. Basically, it's getting ready to start replicating data to our Ohio cluster, right? So it's going to take about 10 minutes for this Ohio cluster to be up and running, where we'll be creating those instances and stuff. And then, it's going to take a little bit more time for it to, replicate the data. But the Lambda function has completed, right? It just converted Virginia to a global cluster as a primary cluster within a global cluster, and added the secondary cluster that we provided as input as a secondary region to that global cluster. And you can see that this Lambda function also successfully completed. So that's our first use case that we just discussed about automating DR. So let's go back to our presentation to take a look at the second application of the solution, which is for business continuity planning. Okay, so hope you found that demo useful. The DR use case that we just discussed helps to address unplanned outages. I also hear from customers that they have a need for planned failovers to meet their business continuity planning requirements. The solution we have created addresses this needs as well by calling the two Lambda function that we just discussed in the previous slide in sequence. So this solution introduces a new Lambda function called failover and convert to global. And this Lambda function takes the global cluster ID as input, very similar to what we discussed in the previous slide, along with the secondary cluster to be promoted with its Route 53 hosted zone ID and the CNAME that is used by the application. This function then scans the cluster topology and creates a snapshot of the topology before triggering the failover to secondary Lambda function. So this snapshot will be used by the solution to create inputs for the convert regional cluster to global cluster Lambda function. So after the first Lambda function, the failover to secondary successfully completes, the solution converts the promoted cluster to a global cluster. And the secondaries of this global cluster will be the remaining clusters from the original global cluster. So let's say you started with the primary in US East 2 with secondary in US West 2. This function will create a global cluster with the roles reversed, right? So basically you'll have a global cluster with primary in US West 2 and secondary in US East 2. And let's look at a demo to understand this better. Let's navigate to the AWS console and see how the business continuity planning demo looks like. All right, so now I'm here at the AWS console. I'll start with the third Lambda function, which is called failover and convert to global, which we just saw in that architecture diagram. I'm going to trigger this process as well. And what this does is it takes a global cluster. I have another global cluster called global cluster, and it has a secondary cluster called East 2. And same inputs like before for the primary cluster, CNAME, and the hosted zone ID. So if I go over here, you can see that the global cluster called global cluster exists here, and it has East 1, which is the primary, and East 2, which is a secondary cluster. So we triggered the failover and convert to global cluster Lambda function, which as a first step will call the failover to secondary, which will bring this East 2 as out of this global cluster, which will remove the East 2 from the global cluster and promote it as a standalone primary cluster. So you can see that it started the promotion process. And after the promotion process completes, remember this function takes a snapshot. So it knows that there is an East 1 cluster and an East 2 cluster. It also knows that East 1 belongs to a specific VPC. It has specific security groups, subnet groups, and cluster parameter groups and all that. So it takes a snapshot of the topology. And when it calls the second function, the convert to global function, it passes all those as inputs. And the net outcome is you would still see a global cluster with East 2 as primary and East 1 as secondary. Now, this process does take time, right? It takes about 10 minutes because what we are doing is we are removing East 2 from global, we are deleting the East 1, and then we are adding that East 2 back as the primary and adding a new East 1 cluster as secondary to it. So this process is going to take about 10 minutes time, but at the end of it, you would see the roles reversed with East 2 as primary and East 1 as secondary. Right. So just a quick refresh, and you can see that East 2 is already gone, and East 1, this global cluster and East 1 is still here. But if I go to East 2, you would see that our East 2 cluster has been promoted to a standalone primary. Right now, in a bit, this East 2 cluster should be added back to the global cluster, like you see over here. It's added as a primary to the global cluster. And if I go to East 1 now, the other cluster, East 1, the old East 1 should be in a deleting status. There you go. The old East 1 is in a deleting status because we don't need this old East 1 anymore because we're not going to be able to go back to that East 1. So we're just cleaning it up. And in our global cluster, we are adding another East 1, right? I'm just appending a timestamp just to maintain uniqueness for the cluster identifier. But if you look at it, this is the net of it, right? So I still have the global cluster called global cluster. East 2, which was originally the secondary, and that's what I passed as input to my Lambda function, is now the primary. And I have a new East 1 cluster, which is going to be the secondary. Right. And this, again, process is going to take a while to create, about 10 minutes. But if we go back to our Lambda function, we should see that it's completed. And I get this message successfully failover and converted to global cluster. So that's the last Lambda function or the failover and convert to global Lambda function, which comes handy for a BCP or business continuity planning use cases. So let's go back to our presentation and take a look at our recent releases. Hope you like the demo. Before I wrap up today's session, I would like to highlight some of our recent releases. We recently launched free trial for DocumentDB. You can now try Amazon DocumentDB for free with a 1-month free trial. This will allow you to evaluate DocumentDB for your needs without worrying about the budget. Graviton instances were launched late last year. They provide better price to performance improvement. We see up to 30% improvement in performance and 5% reduction in cost with these Graviton instances. RBAC, or role-based access control with user-defined rules, was introduced late last year, and this lets you define custom rules for controlling access to the data. So we discussed global cluster and how it's ideal for disaster recovery use cases for applications with strict RTOs. These were also released around summer of last year, and has been quickly adopted by our customers now. AWS backup integration allows you to centrally manage backup of your AWS database services. Being a native AWS service, DocumentDB integrates with many other AWS services, and AWS backup is one of the recent services we've added to our stack. That brings us to the end of today's webinar. As promised earlier, here's the link to the automation solution we discussed in this webinar. Please feel free to give it a try and let us know your feedback. We will continue to work backwards from our customers' needs and build solutions to address your requirements. I want to thank you for your time and attention. I'll now open the session for any questions.